Welcome back from intermission. My name is Sinclaire Manning, aka Major Merger.
I am Dr. Brian W. Mulligan, also known as Astrobit.
And we are here to present you this month's top news stories in astronomy. Ow! First up, dust around Mercury. So, two dusty discoveries may shake up our understanding of the inner solar system. A recent study suggests that Mercury shares its orbit around the sun with a big ring of dust. Another paper concludes a similar halo of dust and yet to be discovered asteroids exist around in the orbit of Venus, which are both seen in this artist's rendition with the sun in the middle and then the Mercury, Venus, Earth coming out from there. So researchers originally thought that Mercury, unlike Earth and Venus, was too small and too close to the sun to capture a dust ring, and expected solar winds and magnetic forces from the sun to blow away any dust at Mercury's orbit. But Guillermo Stenborg, a solar scientist at the Naval Research Laboratory in Washington, D.C., and colleagues have shattered this expectation after analyzing images captured by one of NASA's twin solar and terrestrial relations observatory spacecrafts. So the researchers initially were working to create a model based on these images to understand the dust that could interfere with data taken by other spacecraft, like the Parker Solar Probe, which is making its closest flyby around the sun. But when they applied their model to the images, they found much more dust than originally anticipated. And regardless of where the spacecraft was positioned taking its images, they saw the same 5% increase in dust brightness and density, showing that this ring of dust extends all around the sun. So the team calculated that the dust ring is about 9.3 million miles wide, and the next step for astronomers will be to figure out where the dust in these rings come from, with the most probable culprit being a population of undiscovered asteroids zipping around the sun at an orbit similar to Venus. Yeah, mystery asteroids.
Out at Venus, not right by Mercury, but out at Venus.
Yeah.
Oh, wow.
But hard to see because the sun's so bright, obviously. Yeah.
Are they going to be demoted because they don't clear their orbits?
Yeah.
You know, I was wondering the same thing when I read that article myself. So we no longer have any planets on our solar system is the answer.
Yes.
We're all minor planets. Exactly. All right, so a recent study led by Marcin Turbet of the Laboratoire de Météorologie Dynamique in Paris, France, have found that rain on Mars could have been caused by giant asteroid impacts. So early in the solar system, the sun was a little bit dimmer and cooler than it was in the current day. So at the time, Mars was likely not warm enough to have a rain cycle like we have here on Earth. But there's definitely clear evidence of erosion and dry river and lake beds on Mars early in its history. So one possible explanation, is that better? Sorry. So one possible explanation for rain on early Mars is heating through giant meteors hitting the planet. So the study led by Martin performed three-dimensional simulations of the atmosphere and water on early Mars. When a large meteor impacts the planet, it vaporizes water on the surface where the meteor impacts. And the vapor and the impact heat the atmosphere. Initially, this forms clouds, and the atmosphere is too hot for it to rain. But after about half a Martian year, the atmosphere cools down enough, and it starts a very, very, very long monsoon season lasting about 12 Martian years. So long term of rain. Over that time, about 60 feet of rain fall throughout the surface of the planet. So yeah, a really bad, not a whole lot of fun. So after this, the rain finally stops, the clouds persist, which lead to cooling of the planet. And this leads to a slow freeze taking hundreds or thousands of years, and then the clouds finally dissipate over the next million years or so. So the study doesn't explain all aspects of rain on Mars or on liquids on Mars. So the large valleys and canyons systems that are found near the equator of Mars, such as Valles Marineris, these regions actually receive a lot less rainfall according to their simulations. So clearly are not this particular aspect of meteor impacts causing rain is not responsible for those particular systems. So obviously something else is causing rain or was causing rain on the surface of Mars billions of years ago. So further study will be required to understand that.
Whoever purred, I like that reaction. Yeah. All right, astronomers have discovered 83 new supermassive black holes in the early universe. Yeah, yay black holes. So a little more precisely, though, they've detected 83 quasars, which are huge, highly luminous disks of gas and dust that surround supermassive black holes, and they're the part we can actually see. So the quasars and the black holes embedded within them are 13 billion light years away from Earth, meaning we're seeing them as they appeared only 800 million years after the universe first formed. So prior to this discovery, only 17 supermassive black holes had been found in this particular region of sky that's being surveyed. And of the newfound quasars, the most distant one is 13.05 billion light years away, and it is tied with an earlier discovery as the second most distant quasar ever found. So it's very difficult to see, but these are little postage stamps of all the quasars. If you can see a reddish dot in the middle of each of them, that is the quasar. So they're still very faint and difficult to see, but I promise that one exists in the middle, very center of each one of these squares. Okay. So the researchers led by astronomer Yoshiki Matsuoka used the Hyper-Suprime-Cam instrument on the Subaru telescope, which sits atop Mauna Kea in Hawaii. These are important findings for astronomers as they've been working to figure out the main sources that are responsible for reionization, which is a period in the early universe when high-energy photons ionized all the neutral hydrogen. So quasars have been a potential source of these ionizing photons, but this team's work suggests that there are not enough quasars to complete reionization and finish the job. So according to them, there's only on average one supermassive black hole and associated quasar in every cube of space that is 1 billion light years across at this time, so 800 million years after the universe formed. So that's not a lot, and not enough to reionize the universe, as we know.
Lots of galaxies in that space.
There are lots of other galaxies,
Yes,
though, in
yes.
that space, yes.
All right, so a team led by Mikako Matsura of Cardiff University have found evidence of dust forming in the aftermath of supernova 1987A. So supernovae have been long suspected as one of the sources of dust within the galaxy. They expel massive amounts of elements such as iron and silicon, which are responsible for forming much of the dust. However, there's a conundrum in that supernova are also very explosive energetic events that send out shock waves and destroy most of the dust around them shortly after the supernova goes off. So, how is it that these supernova can possibly form dust, but also probably destroy most of the dust around them? So Dr. Matsura's team observes this nearby supernova 1987A using SOFIA, which is an infrared telescope that's built into the side of a 747 jet. It's pretty cool. They compared recent observations that they made with observations of a ring that surrounds the supernova from about 10 years ago. This was supposed to be an animation. Unfortunately, it's not working out, so you could have seen the dust forming. So Google it.
That's my fault. I put the slides together.
I had a feeling it wasn't going to work out. GIFs never work. But anyway, they found that the ring has gotten brighter in the infrared over the last 10 years. So this suggests that the amount of dust that they're observing has increased by about a factor of 50, which is pretty exciting. Such rapid reformation of dust is unexpected, as it was thought that the gas requires another several decades for it to cool enough for dust to begin to form out of the gas. However, there's another possibility that the gas is actually not forming dust, but is so hot that it's radiating in these particular wavelengths and makes it look as though dust is possibly there. So more observations are going to be required to see whether this is in fact dust or if it's just really, really, really hot gas. Dyson has mentioned that they are already setting up a new vacuum cleaner that will be able to clean all this up. It's only going to cost $10 trillion.
Can we put a microphone on it? Thank you.
$10 trillion plus $10.
Okay. I also just realized how dust heavy our stories are this month. I don't know. Spring cleaning, I guess. All right. So DG-SAT1 is an ultra-diffuse galaxy, meaning it's as big as a typical galaxy, like our own Milky Way, but gives off very little starlight. So on the right, you have a typical galaxy, and on the left is DG-SAT1. Can you see it? It's there. In that region, yes, there is a galaxy. So most other ultra-diffuse galaxies are found within crowded galaxy clusters, and astronomers believe that collisions within the clusters can result in these faint galaxies as their stars and gas are ripped off of them by the gravitational forces of the other cluster members swirling around them. But however, DG-SAT1 is all alone, and without a galaxy cluster nearby, it appears that it has probably changed very little since it first formed. Astronomers studied the galaxy's chemical composition to understand more about the conditions within and around the galaxy. And it turns out that the galaxy has very little iron, but normal amounts of magnesium, which is a little bit odd considering that when stars explode as supernovas, they typically release both of these metals in more or less equal amounts.
Yeah.
He agrees. That's weird.
There should be a lot more iron in there.
So further analysis has shown that the galaxy likely took a long time to form, initially forming when the universe was very young and evolving up until around 3 billion years ago. So this suggests the possibility that this isolated ultra-diffuse galaxy may be a living fossil from the early universe when stars and galaxies emerged in a much different environment compared to what we see today. The team of astronomers led by Aaron Romanowski, a professor at San Jose State University, will continue to work to understand the mystery of how these ultra-diffuse galaxies come to be.
Other way. There we go. All right, so our final story is Astronomy Not in the News, where we cover research that's generating discussion in the astronomical community, but hasn't made it into mainstream news. So this month's story is about a new high-resolution simulation of galaxy formation by a group led by Annalisa Pilepich of the Max Planck Institute of Astronomy in Germany. So this recent simulation zooms into smaller scale than previous simulations by the group, following about 700 galaxies from the very early universe till about 9 billion years after the Big Bang. In universe terms, that's like most of the way along to where we are today. So this particular study focuses on analysis of the shapes and sizes of the galaxies in their study, and their work finds that galaxies tend to have disks of gas around them, around pretty much every galaxy that they find. So the largest galaxies, those closest in mass to our own galaxy, tend to have gas disks throughout the history of the universe. It was not expected that such disks form around every galaxy, as the stars in large galaxies are often seen in large elliptical shapes. So future observations using James Webb Space Telescope and other next-generation telescopes are required to confirm the findings of this group, but it could shed quite a light on where and how star formation occurs in galaxies throughout the history of the universe.
Okay.
All right.
That's all for us.
That's all for
Enjoy the rest of the show.
March 2019. Thank you all for coming. Enjoy.